Hey everyone. So in the last video we were talking about the idea of limiting reactant. We solved some hypothetical examples, and in today's video we are going to try some past paper questions to just compile all the ideas that we have learned so far. We have talked about various formulas for moles, and we have even talked about the idea of how moles in stoichiometry can work with mole ratios and how we can find the ratios from the equation. In the last video, we were talking about even limiting reactants, and we know how to find those as well. So let's start jumping to some past paper questions and see whether we are able to do those or not. This is a question that says K2FeO4 can be prepared in the laboratory by the reaction between iron 3 oxide, which is Fe2O3, chlorine, and potassium hydroxide. The equation is given to us where we can find the mole ratios. So we have the mole ratios over here. Then it says 2 gram sample of Fe2O3. So let's underline this portion. It's about 2 grams of Fe2O3 is added to 20 centimeter cube of 4.00 mole per decimeter cube KOH. So we have the molarity and the concentration for KOH as well. Calculate the amount in moles for Fe2O3. So we have the mass with us. We know how it works. Moles of Fe2O3 is equals to mass divided by the molecular mass. Molecular mass is going to be equal to Fe times 2 plus oxygen times 3, which is 56 times 2 plus 16 times 3. So let's find it out. 56 times 2 plus 48, which is 16 times 3. 160 is the molecular mass. 2 grams divided by 160 should be equal to 2 divided by 160 becomes 0.0125 moles of Fe2O3. Calculate the amount in moles of KOH. So let's find that out. Over here we have the concentration in mole per decimeter cube and volume of KOH. So moles of KOH, which is potassium hydroxide, should be equal to concentration times volume divided by 1000, which means 4 mole per decimeter cube times 20.0 divided by 1000, which should be equal to 4 times 20 divided by 1000, 0.08. So this is the 0.08 moles KOH. The questions continue to ask us which reagent, Fe2O3 or KOH, is in excess in this reaction. We can't just compare the moles right away. We need to find their ratios with the product first, and then we can say. So let's find the ratio of let's do with Fe2O3. So let's find the ratio of Fe2O3 with one of the products. I'm going to select Fe2O3 with K2FeO4 as a product. So the ratio is 1:2. So step 1 would be the ratio between Fe2O3 and K2FeO4. The ratio is 1:2. So our moles were 0.0125. So 0.0125 moles would give us how much? It would give us exactly 0.025 moles of product. This is part 1 of the solution. For the second one, we know that KOH has to be applied with the ratio with the same product. So this time between KOH and 2K2FeO4, the ratio is going to be again 10 times 2. So it's going to be the ratio between KOH over here and K2FeO4. The ratio is 10:2. So if the moles were 0.08 over here, how many moles do we get for K2FeO4? The answer has to be exactly 0.08 divided by 5 becomes 0.016. 0.016 is the answer over here. Which one is smaller? Obviously 0.016 is smaller. So the answer has to be KOH acts as the limiting reactant, is limiting reactant because it produces a smaller amount of product. As it produces smaller amount of product. So that is how we do it. Let's try some other question. This was, by the way, from the summer examination of 2010. Let's try this question. It says, a sample of 0.030 gram of small pieces of magnesium, so we have the data for magnesium over here, is added to 20 centimeter cube of 0.10 mole per decimeter cube hydrochloric acid. So that's the data for hydrochloric acid, the concentration and the volume. Show by calculation which reactant is in excess. So first we have the mass for magnesium. This is the mass for magnesium. So we find the mole of magnesium is equals to mass divided by atomic mass. 0.030 gram divided by the atomic mass of magnesium, which is 24. So 0.030 divided by 24, 0.00125 mole magnesium. We have the ratio between magnesium and the products. So the ratio over here, any product, you can choose any product, whether hydrogen, whether magnesium chloride. I am going for magnesium chloride. So the ratio here is 1:1. So if between magnesium and magnesium chloride the ratio is 1:1, then obviously 0.00125 mole magnesium will give us exactly 0.00125 mole product. So this is the moles of magnesium chloride. This is the first solution step done. Now let's do the same steps, this time with hydrochloric acid. We have the volume for hydrochloric acid and the concentration. What formula do we use? That is going to be CV divided by 1000. So mole of HCl is equals to CV divided by 1000. The concentration is 0.10. The volume is 20 divided by 1000. So 20 times 0.1 divided by 1000. It's going to be 20 times 0.1 again divided by 1000. I messed that up. Yeah, it's going to be 0.002 mole of HCl. Now between HCl and magnesium chloride, what's the ratio? It's 2:1. So it's going to be between HCl and the same product magnesium chloride, the ratio is 2:1. So 0.002 moles can give us how much? It can give us 0.001 mole. So X is equals to 0.001 mole magnesium chloride. Which one is giving us a smaller answer? That has to be HCl. So HCl is the limiting reactant because it gives us a smaller amount of the product, while magnesium is going to be the excess reactant. Magnesium is equal to the excess reactant as it gives us smaller amount of the product. And for further calculations, if someone asks me for the mass of magnesium chloride, I'm going to use the smaller answer. I can never vouch for the bigger answer. Let's try one more question. Now this is actually an MCQ. I made that up. What is the minimum volume of NO2 produced if 60 centimeter cube of ammonia combusts in 75 centimeter cube oxygen? So we have the volume of oxygen and we have the volume of ammonia. We don't know which answer to pick, right? So we will apply the ratio because it's an MCQ. You don't need to find the moles and apply the ratio. If you have watched my mole hack video, you would remember that we can solve volume questions directly. So see, between ammonia and one of the products, let's say NO2. So between ammonia and NO2, the ratio is exactly 4:4, which means 1:1. So if we have 60 centimeter cube ammonia, how much NO2 can be made? Exactly the same, 60 centimeter cube. So this is one of the possible answers for NO2. And similarly, we can do the same calculation with oxygen. Between oxygen and NO2, what is the ratio? It's 7:4. So between oxygen and NO2, the ratio is 7:4. If we have 75 centimeter cube of oxygen, how much can we get for NO2? So we're going to solve it similarly. It's going to be 4 times 75 divided by 7, which is 42.8. So 42.8 centimeter cube of NO2 gas is the second possible answer. Both are NO2. but the 42.8 is the smaller answer. So we always get the smaller value because that's the minimum value. And the answer has to be D for doctor because that is the closest answer. 42.8 can be rounded off to 43. So here oxygen is the limiting reactant because it produces a smaller amount of the product, and obviously ammonia is the excess reactant because it's producing extra product, which is hypothetically doable, but actually it's not doable. So I hope we are clear with this part of the video. In the next video, we'll try more questions. I'm keeping them smaller so that I can obviously retain your attention. So hopefully seeing you in the next video, guys. Thank you.